So let us try to discuss the formulation aspect of quantum mechanics in terms of these postulates of quantum mechanics. So let me recall. I will do it slowly, but uh, please try to follow as much as possible. So first statement that we have made is the state of a quantum system and as I told you that we have kind of at this moment have single particle in mind is represented just give me a minute. I will share that again. Sorry, there was some problem with. Okay, so what I was trying to say is that first statement that we have made is the state of a quantum system, state of quantum system. So I have in mind, of course, a single particle. We'll worry about what happens if more than one particle is there towards the end of today's lecture, but let's at the moment call it a single particle and is represented by a complex valued function of space and time variable. So space and time variables are real. So mathematically, we denote it as some Greek letter, which we can say psi, which is a function of r, comma. R is the position representing space coordinate and t is the time. Then we asked a question that the set of all states, all possible states is a Hilbert space. That means at the least it is a the set of all possible states are set of all square integrable functions. Over and above that, if there are certain boundary conditions, then it has to satisfy those boundary conditions. So you can say that so in general, of course, we know this, and we call this psi of r t, psi of r comma t, call it as a wave function, or sometimes we call it as simply state or state function, or it is also called probability amplitude. And it is Max Born, who gave the following interpretation, that mod psi of r comma t, the square into d3r. This is a volume integral. This is the probability that the system, of course you understand system means the particle, is located in the volume d3r around a point r in space at time. So that implies that if we want to find probability that the system is in some volume V is, so to find this one, we use integral mod psi of r comma t, the square d3r. Now integrate this over this volume V. Okay, and if V is the total volume of interest, if V is the total volume of interest, we have to demand that integral over the volume mod psi of r comma t, the square d3r equal to r. That means in order a function psi of r comma t to represent the state of a particle in volume V, it has to be normalized. This procedure is called normalization. It has to be normalized. So this is one, in some sense, I would call this as a discipline, because many times uh, in competitive exams, people will try to check whether you have this discipline or not. Okay, so the discipline that you have to have is, before you use the wave function for any calculation, for any calculation, first check if it's normalized. Is normalized. If not, normalize it before using. That means in quantum mechanics, you have to use only normalizing states. If the state is not normalized, then this integral psi square d3v. Okay, so if psi is not normalized, if psi of r comma t is not normalized, then integral over that volume of interest, psi of r comma t modulus square d3r will be some value less than infinity. Then define some psi tilde of r comma t as 1 over square root of n into psi of r comma t. Okay, so this is normalized. So that integral over volume psi tilde of r comma t mod square d3r is equal to 1. So use psi tilde of r comma t for all calculations. So this discipline is very important, and many times, if you don't know this, so in competitive exams, what they will do is they will try to give a state which is not normalized, and they will ask you to calculate some probability. Then if you use that wave function, you will get a wrong answer, and as such, the answer that you get will be there in one of the choices in multiple choice questions, and that is how you attract negative mark. So this discipline is the first very important discipline that you have to learn or inculcate with the first postulate. So this is what is that we discussed with respect to the state of the system. Now, secondly, we talked about operators and physical observables. Physical observables. Physical observables of quantum system. Quantum system are represented by self-adjoint operators operating on Hilbert space. Basically, Hilbert space is the set of all states and the self-adjoint operators operating on this Hilbert space. So we have seen last time that the self-adjoint operators, I will use self-adjoint and Hermitian interchangeably, and that is what you find in textbooks. But whatever small difference that I mentioned in the last class with respect to self-adjoint and Hermitian is when you go from finite dimensional vector space to infinite dimensional vector space. So let's assume that uh, we will say self-adjoint and Hermitian we will use interchangeably. And please understand that the difference is only in some specific cases. Okay, so we have proved two things. That is eigenvalues of a Hermitian operator. Hermitian operators are real, and eigenfunctions eigenfunctions of Hermitian operator with distinct eigenvalues distinct eigenvalues are orthogonal. Okay. So we have proved this last time, but I said we have to have this distinct eigenvalues uh, as a requirement. Now, what happens if the eigenvalues are not distinct? Okay, so if the eigenvalues are equal, okay, so for example, for some eigenfunctions, say some eigenfunctions of operator A, say from phi m1 of x and phi m2 of x, eigenvalue is same. Call it E. Okay, so then we say that EM, I was calling it as AM, right? So AM. Then we say that AM is twofold degenerate. So the word used is degeneracy or degenerate. Okay, so it is twofold degenerate because there are two functions. If there are three functions for the same eigenvalue, we say threefold degenerate, and so on. So this particular theorem or this particular proof what we gave yesterday does not guarantee that this phi m1 and phi m2 are orthogonal. So that phi m1 of x and phi m2 of x are not necessarily orthogonal. Necessarily orthogonal as per the proof given. because the proof given was only for distinct eigenvalues. If the eigenvalues are same, then we cannot say that they are orthogonal. But notice that note that some C1 times phi m1 of x plus some C2 times phi m2 of x. Okay. So what happens if I operate A on this? Okay, so I will leave it for you to check. Note that is also an eigenfunction. An eigenfunction of A with the same eigenvalue. The same eigenvalue A. So I request you to verify this. You have to operate A on this and make sure that this is the case. Okay, for arbitrary complex coefficients, C1 and C2, such that modulus of C1 square plus modulus of C2 square is equal to 1. Okay, assuming that this phi m1 and phi m2 are already normalized. Okay, so that means what? If there is a degeneracy, okay, so AM is twofold degenerate. AM is twofold degenerate. That implies there exists a vector space. There exists a subspace defined as span of phi. I don't know if I introduced this terminology, phi m1 of x and phi m2 of x. Span of these vectors, that means this is basically set of vectors like this: C1 phi m1 of x plus C2 phi m2 of x, such that C1 comma C2 are complex numbers and modulus of C1 square plus modulus of C2 square is equal to 1. So how many such vectors are there? There are infinitely many such functions are there. Phi m1, phi m2, and I have C1, C2 are arbitrary. I can take any. Okay. So phi m1 and phi m2 are not orthogonal, but they are linearly independent. They are linearly. Otherwise, it is not degenerate. It is degenerate means what? There should be two linearly independent functions with the same eigenvalue. So if they are linearly independent, then you can construct a vector space which is called the span of these two linearly independent vectors, and this vector space will become a two-dimensional vector space. So this will become a subspace to the state space. Okay, this becomes a subspace to the state space. So that means every vector in this subspace is an eigenstate of A with the same eigenvalue AM. Okay, so let's call this as some VM. So every function every function of Vm is an eigenfunction of A with the eigenvalue, same eigenvalue basically, eigenvalue A. That means there are infinitely many vectors in this subspace. So whenever we have a degeneracy, then we have not two vectors but two-dimensional vector space. Okay, so we say that this Vm is basically an eigen subspace of Am, eigen subspace of Am, which is a subspace of the Hilbert space H. Okay. Now that so suppose if you have threefold degeneracy, okay, so note that Vm is two-dimensional because they are two linearly independent. Okay, it is two-dimensional. If we have threefold degeneracy, then we have three-dimensional. So in general, if Am is some f-fold degenerate, if it has f-fold degeneracy, then Vm, that is the eigen subspace of Am, is f dash.
Sir,
Yes.
is there any proof to we can say that this is the case? Like if AM is F4 degenerate, then we have AM's eigen subspace is n dimensional. Is there
Proof is
any?
just by construction. Because suppose if I have f-fold degenerate, then I'm going to have linearly independent functions like phi m1 of x, phi m2 of x, etc., phi mf of x. So these many functions will be there. All of them are having the same eigenvalue am. Now you simply have a span of this. Okay, span is always a vector space because by construction it is a vector space. Okay, so this is a subspace. It is a subspace of H. And this is a vector space, and this vector space is f-dimensional because there are f linearly independent vectors. Okay, so that is what it is. You can actually construct an f-dimensional subspace such that all the vectors in that subspace are eigenstates of A with the same eigenvalue.
Okay, sir.
If you understand this construction or this thing, then it even though phi m1, I'm going back to two-dimensional vector space. Phi m1 to x and phi m to x are not orthogonal. We can choose a pair of orthogonal states. We'll call them as, let's say, phi m1 tilde of x and phi m2 tilde of x in Vm. Because we have infinitely many states, in that I can choose some two states which are orthogonal states. And then, so in my description of the states, so let's say I have eigenvalues here, eigenvalues and eigenfunctions. Suppose if I am writing a tabular column of eigenvalues and eigenfunctions, let's say A1, I have phi 1 of x, and A2, I have phi 2 of x. So these are all non-degenerate. But when I come to AM, okay, so I have two states, phi m1 of x and phi m2 of x. Okay, so these are the two states corresponding to this AM. AM is twofold degenerate. Now the point is that our proof that we gave, phi 1 and phi 2 are orthogonal. If the eigenvalues are distinct, they are always orthogonal. Only this we are not sure. So what I am trying to say is, since there is going to be an eigenspace, you can always choose some phi m tilde of x, phi m1 tilde of x, and phi m2 tilde of x. Okay, how to find this out is easy, because what you have to do is this phi m1 tilde of x will be some kind of a c11 times phi m1 of x plus c1 c12 times phi m2 of x, and this is going to be c21 into phi m1 of x. This is going to be c22 of phi m2 of x. Okay, so you have to demand that this inner product of these two, phi m1 tilde and phi m2 tilde, should be 0, and then you should find c11, c12, c21, c22 such that that is satisfied. That's all that we are going to demand. Okay, so it is possible to find that, and therefore the claim that I'm going to make here is, eigenfunctions of a Hermitian operator are orthonormal. So this term orthonormal has two properties. One is they are orthogonal, and second thing is they are normalized. Okay. Now these two conditions mathematically can be represented in this following. Suppose if I take phi m of x, comma, phi n of x. These are two eigenfunctions of A. This inner product is equal to delta mn. This is called Kronecker delta. So this means if m is equal to n, this is phi n is equal to 1. That means it is normalized. If m is different from n, then this is um, orthogonal. So eigenfunctions of Hermitian operator are orthonormal. Okay, the orthogonality property only, I told you that if they are distinct eigenvalues, we have proved it. If the eigenvalue is same, I gave this argument to say that it is not guaranteed, but you can always construct orthogonal values. So it is always possible to construct a set of eigenfunctions of Hermitian operator that are orthonormal. Okay. Now we have an interesting situation. So suppose, let's say we have, so let's say that, so let this H be a Hilbert space. So this is basically, it's a functional space. Remember, this is a functional space of functions. right? That means it is infinite dimensional. Infinite dimensional. Now, what kind of infinity is that? It is basically an uncountable infinity. Uncountable infinity. Now, what we can talk about, what we can say about the basis of such a space. Basis of such a state. For example, suppose if you uh, so let us talk a little bit about the basis of H. Like we discussed from the context of this one, that is from the analysis that we did with R. Shankar's R. Shankar's example. Suppose if I have 0 to 1, then let's consider set of all functions between 0 and 1. Let's say this is one function, and there is another function like this. So I call this as f, this as g, like that. So now f of x, that means I have vector space here where these are functions f of x such that um, x belongs to 0 comma 1, and the function is from 0 comma 1 to some complex numbers, instead of all complex numbers. Of course, I'm plotting it, but uh, I can in principle say that this is from 0, 1 to complex numbers. This is my vector space. Now, if this is the vector space, what is the component? So first, I understand that this is infinite dimensional. Infinite dimensional. Why this is infinite dimensional? Because I require the value of the function at every point in the x. Okay, so that means every point. Okay, so every point in interval 0 comma 1 is a basis. Okay, every point between 0 comma 1 is a basis. Now this basis is what we call as a continuous basis. Thus, I can say that so the value is like I can say I can represent that by x, and x is between 0 and 1, like that. So there is a continuous basis. But I can also have a situation, okay, so continuous basis. So this is something which we have understood earlier. Now suppose A is a Hermitian operator. A is a Hermitian operator. A is a Hermitian operator. And if A is a Hermitian operator, then eigenstates of A, okay, so phi m of x, m is equal to 1 to infinity. So there are infinitely many m, are eigenstates, eigenfunctions, eigenfunctions of A, eigenfunctions of A with eigenvalues. This set I will call it as some AEM. Okay, these the eigenfunctions. Now these are also infinite, but they are discrete. I mean, they are infinite but countable basis. It's not a continuous basis. Okay, that is this phi 1 of x, phi 2 of x, etc. is is denumerable basis. enumerable set. Okay, enumerable set. Now there is a concept called completeness of a basis. What we discussed earlier was the completeness of a set. Okay, so completeness of a basis. Okay, again, every basis is complete in finite dimensional Hilbert spaces, but only when you go to infinite dimensional Hilbert spaces, this is required to be addressed. So, what is the completeness of the basis? So, before we understand this completeness, let me go back and then try to represent our three-dimensional vector space. So, consider R3. Okay. So, let's say I have this I. So, let me represent this vector as a ket. I is equal to 1, 0, 0. J is equal to 0, 1, 0. And K is equal to 0, 0, 1. In the vector notation, we have written this ket in this fashion. Now we will define something called an outer product. We have talked about inner product. Now we will define something called an outer product. So what is an outer product? Suppose if I have I and I multiply this with I like this. Okay, what does that mean? That means I have 1, 0, 0, and then I have 1, 0, 0. Now, in matrix multiplication, we do not know how to do this because this is kind of a 3 by 1 matrix and this is 1 by 3 matrix. So, what we should get? We should get a 3 by 3 matrix. So, how do we do this multiplication? Is something like this. You take this 1 and multiply with this row and then write this as 1, 0, 0. Then this 0 is multiplied with this and write it as 0, 0, 0 and 0, 0. Okay. Now, if you ask what is J outer product J, then you have 0, 1, 0, 0, 1, 0. That will be 0, 0, 0, 0, 1, 0, 0, 0, 0. Similarly, if you have K outer product with K, then you have 0, 0, 1, 0, 0, 1. This will give you 0, 0, 0, 0, 0, 0, 0, 0, 1. Now you ask what happens to this quantity, that is I plus J plus K. Okay, this is a three-dimensional system, a vector space, and hence three basis vectors. When you take outer product of all these, is also called some projections. So projections of all these basis elements will be equal to identity. Okay, so whenever you can write down the resolution of identity by the basis elements, then we say that the basis is complete. Okay, so this is called resolution of identity in terms of orthonormal basis. If we can do that, then we say that basis is complete. Basis is complete. Now, you can say, so here I am going to make a statement whose proof I will not give now, but probably it is mathematically a little involved. So let me just make a statement here, or let me make a claim. The claim I'm going to make is that eigenfunctions eigenfunctions of every Hermitian operator form a complete orthonormal basis of the state space H. Now remember that this is of course true with every Hermitian operator. Okay. For example, let us try to here we will try to use or convert to this Dirac notation. So let me say a few words about this Dirac notation. Okay, a state is represented as a ket. Okay, so we are going to represent this as some psi. Okay. Now, if a basis is chosen, okay, so it can be realized as a column vector, a column matrix. It can be finite or infinite, depending on the case, finite or infinite, once we choose a basis. Okay. Now let us say that we have. So now let us consider. Uh, so note that position is a physical observable. Note that position is a physical observable. That means, so there is a Hermitian operator corresponding to it. Now, what is that position operator? Suppose if I take X and I call it as an X operator, okay, it is defined as, remember, we are going to define this. We are going to define it as when X operator is acting on some psi of X, it is going to be, this is a definition. Okay, X acting on psi of X is simply X multiplied by psi f. Okay, so this is the definition. Okay. Now I want to represent. Okay. So now let's say that position operator is x. So x is the position operator. X cap is the position operator. Okay. Now, what are its eigenstates? Okay. So, what are its eigenstates? And before we ask eigenstates, what are its eigenvalues? Eigenvalues. Now, eigenvalues are like what is the they are basically position values, right? So that means every value of x is a position value, right? Eigenvalue of x is every x. Okay, so um, so every x in the real line is an eigenvalue. That means the eigenvalues are not discrete, but they are continuous. Okay, they are continuous eigenvalues. And corresponding to every eigenvalue, there will be an eigenstate. So let us denote the eigenstate. Denote the eigenstate, or we call this as a position eigenstate. Position eigenstate as a ket vector x. Okay. Now, please understand what I am writing here. Suppose I have an operator x. When it is operating on a ket vector x prime, I will get an eigenvalue which is called the x prime. A ket vector x, when operates on an eigenstate x prime. Okay. Remember, this is a general operator. So this is an operator. This is an operator. Okay. And x operating on x prime is variable. X prime can be x prime or x double prime. So whatever is there inside the ket, that will come out as the eigenvalue. Okay. So now if we understand this, then we can say that this set of all these kets x, okay, is a continuum basis of h, because x is a Hermitian operator, continuum basis. And what kind of basis it is? It is a basis which is complete orthonormal basis. Okay, so this is a complete orthonormal basis. Now we have to define this in the case of continuum basis. Okay, so let's try to understand this. Orthonormal means, suppose if I take a vector x, and then if I take another vector x prime and take their inner product x prime. Okay, if x is equal to x prime, then it has to be equal to 1. That is what is called normalization. If x is different from x prime, then it should be 0. But this is continuous. Okay, there are no discrete indices. So that is where you have to use what is called a Dirac delta function, which is a continuum version of this Kronecker delta function. So this is the statement of orthonormality. In a continuum basis, if you want to talk about orthonormality, we use Dirac delta function. What about completeness? Completeness is just like here you have this I, j, j, k, k. We have summed it in this case, but now this is a continuous thing. So what I have to do is I have to integrate minus infinity to infinity the outer product of x, x, and then I integrate over entire dx. That will be equal to my identity. This is resolution of this is the property of completeness of the basis, the completeness property, and this is an orthonormality property. So now we are ready to, if we define this, then we are ready to understand what is the connection between this ket vector or a ket and a wave function that we have been talking so far. Now let's say that let psi be a general element of H, a general element of the Hilbert space H. Now I can write this psi as, let's say, identity operating on psi, because identity operating on psi, nothing will happen. Identity is not doing anything. But now let's say that I, instead of this identity, I put in this. Okay, so I can write identity as this one, right? So this is nothing but I can say integral minus infinity to infinity x, x, and then psi dx. Okay, so now you can see that this particular term is an inner product of psi and x, correct? It's an inner product of psi and x. What is that? In general, if you take inner product of two vectors, this will be some complex number, right? This will be some complex number. So we are going to call that complex number minus infinity to infinity. I will call that complex number as psi of x dx. Now you see, what does that mean? That means when we choose the basis as the eigen eigenstates of position operator, eigenstates of position operator, then psi can be expanded in that basis. Expanded in that basis, as we have seen in this equation. Okay, like in this equation, where psi of x is the component, psi of x is the component of psi, psi of x is the component of psi along x. Okay. Now, just to understand this a little more clearly, suppose if I have a vector, okay, so let us consider, so look at R3 again. Look at R3 again. Look at R3 again. Suppose if I have a vector V, which I can write it as V1 times I plus V2 times J plus V3 times K. Now these I, J, K are orthogonal vectors. Okay, so I want to get V1. How do I get V1? I take I inner product with J, then I will get V1. Because I inner product with J, I inner product with K is 0, so I will get V1. So that means what? This implies V1 is a component of V along which direction? Along I direction. So same thing is what is happening here. This so basically this is x psi. Okay, so x psi is psi x. Now I want to get psi of x, then what I should do? I should simply take an inner product of this psi with x, then I will get psi of x. So, so with this analogy, we can easily understand that psi of x is obtained by taking inner product of x with psi. This is the correspondence between whatever wave function that we are talking and Schrodinger equation and then the abstract Dirac ket. Now the point is that so essentially the wave function, so when we work with wave function, so when we work with wave function, that means we have already chosen our basis, that is coordinate basis, position basis, coordinate basis or position basis. Okay. So now suppose I don't want to choose a position basis. I want to work in basis independent structure. That means we should not work with so if you want to work in a basis independent abstract version, then we work with ket, only ket vectors. But whenever you want, you can always take an inner product with the position, then you will get the wave function. Okay. Now the point is that coordinate basis is only one of the bases. Coordinate basis is only one of the bases. Now we can choose another basis. For example, let's consider momentum basis. So let's consider momentum, linear momentum. Linear momentum. That is your P. It's an operator, the Hermitian operator, P operator. Now we can have states, which I will denote it as P. Okay, so these are eigenstates of P. Now they are also continuum basis. Okay, so this is another continuum basis. Another continuum basis. The moment we have another continuum basis, what does that mean? That means we have orthonormality. That means when you take some P prime E, that is given by delta of p minus p prime. This is your Dirac delta function. And then integral minus infinity to infinity p outer product p in integrate over dt that is equal to identity. Okay, so this forms a complete orthonormal basis. Okay, so let us try to write that in shorthand notation as CON, complete orthonormal basis. So this is another operator, and corresponding to the eigenvalues and eigenvectors of that operator, will also have a complete orthonormal. Okay. Now we can ask the following question. We can ask the following question. The question is, suppose consider a momentum eigenstate. Consider a momentum eigenstate. Consider a momentum eigenstate. I will call it as P. Okay. Now we ask a question: what is the component? What is the component of E along X in position basis? Okay, we can ask that question because this question is basically valid for any state, right? So, we said if we work with psi of x, we have already chosen our basis. So psi of x is component of. So I have written it here, right? So psi, the eigenstate of position operator, the psi can be expanded in terms of this, and psi of x is the component of psi along x. Now I am asking, instead of psi, I have p. What is the component of p along x? In other words, I'm asking what is the uh, wave function? What is the wave function of momentum eigen state? Or what is the momentum eigen function in the position basis? That's what we are asking. Now you can, so essentially we are asking this question. I have an inner product of x with p. What is this? This is the question that we are asking. Now this can be done in two ways. Okay. So first way is that this is essentially, we want to have a wave with fixed p, and then which implies fixed wavelength lambda, that is equal to h by p. Okay, so such a wave is a plane wave. Is a plane wave. Okay, so physically we will motivate that this wave function has to be related to some kind of a plane wave. So we can say that this is equal to e to the power I. You have this 2 pi x by lambda. Usually any wave which has a wavelength is called 2 pi by lambda into x. So the 2 pi by lambda, we will call it as k into x. So e to the power k. So this is, I mean, by physical argument, we can associate this kind of a function. Okay, so this is one way to argue, because the basic things we have to first identify. Okay, earlier also we argued that the plane wave has to be the wave corresponding to, if you recall, when we talked about Schrodinger equation, when we tried to present a heuristic argument for the Schrodinger equation, we said that it can be written as a plane wave, because the plane wave is the one which has got a fixed value of the wavelength, or the single wavelength, or a single momentum. Okay, so that is one way. The other way that we can think of is, suppose I do not know what is this wave function. So let me call this as, so let us say that this is some function, so which I will call it as some f of x. I could have called it as p of x to be consistent with what we've been writing, p of x. Now we will try to use the operator identification. Use the operator E, denoted as minus IH cross d by dx. Okay, when we discussed Schrodinger equation, we identified an operator correspondence between p and x. So this is the operator in, of course, in terms of the position. Okay, so if you use this, then you can ask a question. So suppose I have this operator p acting on this p of x, I should get some p into p of x. This is the statement of an eigenvalue equation, right? So that means this implies minus IH cross d p of x by dx is equal to p into p of x. Okay, so you can simply write this as dp of x by p of x is equal to I by h cross. I have minus 1 by h cross. I take I to the numerator into p. Okay, so into dx. So you integrate this one, you get logarithm of p of x is equal to I by h cross into ex. Okay. And of course, there will be some constant. So let's call this as logarithm of some constant c. So you get p of x is equal to some constant exponential of c, we'll call it as some a into e to the power I by h cross into px. So which is equal to a into e to the power I, p by h cross I will call it as k into x. Okay, so that p is equal to h cross k. Momentum value is related to k in this fashion. So this is another way in which we can understand what is the component of p along along this direction. So that is e to the I kx. Now there is, so we have talked about two operators, namely position operator and momentum operator, and both operators have got continuum of basis. So we have said how to understand orthogonality in this, how to understand completeness relation in this. Now we can also think of having an operator A. So consider another Hermitian operator, operator A. Okay, so I mean, if you want, you can say this is like energy. So energy is a property of the system, and there will be an operator corresponding to energy. So let's say we have an operator A. Now this operator A has got discrete eigenvalues. That means I have something like this: A phi n of x. Okay, let me use this notation. So A, I have some phi n is equal to a n phi n. So these are eigenstates of A, with the eigenvalues am. But the difference is that this phi n is a denumerable set. It's a denumerable set. That means it is not a continuum, okay, denumerable set. But what I made a claim here, if you go back and then look at the claim that I have made, eigenfunctions of every Hermitian operator form a complete orthonormal basis of the state space H. That means this also forms a complete orthonormal basis. Now, what does that mean? That means this also forms a complete orthonormal basis. What does that mean? That means you have phi m, phi n is delta mn. This is a discrete version of the orthonormality. So this is basically orthonormal condition. And then what about normalization? Normalization, sorry, not normalization, but the completeness condition is that you take the outer product phi n, and then sum over all possible n, just like I, j, j, k, k that we have talked about. This should be equal to the identity. This should be equal to the identity. Now, this is resolution of identity. This is resolution of identity. Now, this is very important to say that this basis can be used to expand any arbitrary state in this. That is, let's say that let psi be arbitrary. Okay, so let psi be arbitrary. Then we have the same thing that we have done earlier. We can say psi is equal to identity operating on psi, which is equal to sum over n, phi n. So this is identity operating on psi. Now this is a complex number. Okay, so this is a complex number, and we call that number as some Cn. Okay, Cn phi n. So in this sense, what we have is Cn is the component of psi along phi n. The same interpretation, that same thing that we have written earlier with respect to continuum basis, we can also write with respect to this basis. Now, you can see that this Hilbert space has a continuum basis. For example, this X basis is a continuum basis, or this P basis is a continuum basis. Okay. Now, it has also a denumerable basis. It also has what is called a denumerable basis. So that means you have bases like this, phi n. Okay. Now, Hilbert spaces which have these two kinds of bases, in addition to every Hilbert space will have a continuum of bases. In addition, if it also supports a denumerable basis, then we call that such Hilbert space as a separable Hilbert spaces. Okay, we call such Hilbert spaces as separable Hilbert spaces, and most of the state spaces that we have that we work with quantum mechanics are all separable Hilbert spaces. That means they will have continuum of bases, and they will also support denumerable bases like this. Okay, so this is as far as the basis of the space is concerned. So let me go back and then try to present this claim once again, that eigenfunctions of every Hermitian operator form a complete orthonormal basis of the space. Now, some operators may have a continuous eigenstates, some operators may have a denumerable eigenbasis. Whatever it is, this particular eigenspace or this particular eigenfunction set of every Hermitian operator will form a complete orthonormal basis, which implies every quantum state can be expanded in terms of the eigenstates of any Hermitian operator. So this is important thing to note. Okay, so at this point, I think I have underestimated time. Probably we require a part of next class also to complete. So now you see that. So the point that I will make at this moment is that uh, physically, okay. So let's make this point. Physically, when an observable is measured, uh, the result of the measurement uh, belongs to the set of eigenvalues of the corresponding Hermitian operator. So when you measure some property, some observable, so it is something like this. You have a physical observable which is basically a property of the system. Now, corresponding to this one, there is a Hermitian operator. Okay, so this is an element in theory. Okay, and for every Hermitian operator, there are a set of eigenvalues and eigenfunctions. Okay, so you have set of Hermitian operator. Let us call A. So Hermitian operator A. Let's call this AN and set of all eigenstates phi. Okay, so they exist. Now let's say that you measure. So you measure this property. Measure using a meter. Okay, some meter. Okay, so the result belongs to this. The meter reading will be one of the eigenvalues of this. Okay, so this is the correspondence between elements in theory and then physical observations. Result will be one of the eigenvalues of the Hermitian operator. Now the question is that a very important aspect of quantum mechanics comes in here, that uh, the result cannot be predicted. Results cannot be predicted. Okay? The result can be result will be one of the eigenvalues occurring randomly. Okay, so this is very important. Randomly, this is very important because this is also the source of a lot of discomfort. We don't want anything to happen randomly. We should have control, but we seem to be we don't seem to have control, and the results are not in our predictive power. We don't have any control on the result. It occurs randomly. Okay, so this is what we gives rise to what is called indeterminism. That means we do not know what will be the result. We can only say what are the possible results. Possible results are the eigenvalues. So this is essentially the crux of indeterminism in quantum mechanics. Now, what we know in quantum mechanics is that so the system is in, uh, let's say the state of the system is, let's say, psi. So when you are measuring this physical observable, the system is in state psi. Okay. Then, as we know that this the eigenstates of A form a basis, we can imagine that the psi, we can express psi as sum over n, Cn phi n. We can write it like that, where the Cn is the component of psi uh, along phi, so which is essentially the inner product of phi n with psi. Okay, so we know that. Okay, so what we can predict or what we can calculate. Okay, so now you can say that the result is going to be one of the eigenvalues. Okay, so you can ask a question. The result is an. Okay, the result is an with a probability modulus of Cn square. It is the phi n psi. This is Cn and modulus of the square. This is the probability that you get the result an. So what quantum mechanics gives you is these probabilities. Okay, so you can say that you have result a1, a2, etc., some an, and so on. So you can say this probability of this one is mod c1 square, probability of this one is mod c2 square, probability of this one is mod cn square, and so on. So these are possibilities or possible results, and these are probabilities. Probabilities of possible results. Okay, so this is precisely what quantum mechanics gives. So we work with quantum mechanics only in terms of finding the probabilities. We do not know what is going to be the result. Okay? We only know that the result will be this one, this one. Just like we know when we toss a coin, we do not know what is going to be the outcome of the toss beforehand. But we can say that the probability is head with the the outcome is going to be head with the probability half, or tail with the probability half. Or if you engineer and load the coin in such a way that the probabilities are altered, you can say that the probability that this loaded coin will show head is some p, and that it will show tails is 1 minus p. So that's all that we can say. And we know these probabilities does not mean that we know anything about a given task. In the same way, knowing these probabilities does not mean that we can predict the result of an experiment. Now, what happens in general is the following. Suppose if you say that you have so system system state is, let's say, psi, then you measure A, then at this level you remember that you have this kind of a situation, sum over n cn phi n. Now imagine that we have a source. Okay. So I have a source here which will generate particles. Okay, particle by particle it is sending. Now all these particles are in state psi. This is in state psi. This is also in state psi. Like that. All of them are somehow prepared in this state psi. Okay. So, so this is what is. So I have a stream of particles all prepared in state psi are coming. And now here there is an experimenter, an observer sitting with something called a meter to measure this property called A. Now what happens? The readings of this meter, okay, is going to be random. Okay, so the meter readings can be, first one is A1, second one is A9, third one is A12, okay, and so on. Maybe they have A 10,000, 1048, A23, like this. So they are random basically. Okay. That means each one of the particle, even though it is in the same initial state, when you measure it, you will get different eigenvalues. This is the reason why we are not able to predict. But then you ask a question that what is the number of times? Let us say nj. You define it as number of times aj occurs as result. And then ask what is this nj divided by total number of experiments that we have done. In the limit this n goes to very large, this will be equal to your modulus of Cj square. That is the probability of Aj. So this is equal to your probability of Aj. Okay, so this is what you can get. Now at this point, I would like to use a language that in this case we say that A, that is this observable, is dispersed in time. So I will use this language, and I want you to also notice that it is dispersed means what? All measurements of an identically prepared states is not giving the same value. So there is a dispersion. Dispersion is essentially spread. So there is a dispersion in the results. So A is dispersed inside. Okay. Now suppose I have another situation where the source the source is now giving these particles. Okay, these particles. Now let's say these particles are in state some phi phi j. This is in state phi j. This is in state phi j. This is also in state phi j. Let's say the particle is preparing this with the state phi j, phi j, phi j. Now let's say I do the same experiment with some a meter. Okay, then what happens? So your meter readings are going to be AJ, 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 and so on. Every time you do this experiment, you are going to get AJ only, because this is because this phi j is an eigenstate of A. Eigenstate of A with eigenvalue AJ. Okay, so here I can even predict. If I know phi j, I can predict. Okay, so the result can be predicted here. The result can be predicted. The result can be predicted. In such cases where you have a particular value which can be predicted, we say that A is sharp. A is sharp in psi. A is sharp in psi. In this case, we say A is dispersed in psi. In some language, people also use another word instead of dispersed. You say that A is fuzzy in psi. Okay, so A is fuzzy in psi. That means you don't get one result, but you get many results, randomly different results. But when you get only one result, you say that A is sharp in psi. Okay, so this is a language which is very useful to keep in mind. And so uh, you have a situation that we know probabilities, and probabilities will definitely lead to dispersion, and we will not be able to predict anything, except that the state in which the particle is coming to the meter is an eigenstate of that corresponding Hermitian operator. So this is some structure that I would like to I would like you to keep this in mind. And so if there are questions, you can ask. I have some more things to complete, but I did not manage completing today. But anyway, it doesn't matter. So in the next class, we will complete it in the first few minutes. Then you can, because we anyway relegated the next class to questions on this. In the initial few minutes, I will try to complete.
Excuse me, sir.
Yeah.
Excuse me, sir.
Like,
Yeah. Go ahead.
sir, I have a question in the chat box.
Okay, if two kits are given, x1 and x2, and we are asked to find an unknown variable m in the x1, considering the two kits are orthogonal and the states within kits are states within ket are orthogonal. When we take both x1 x2 0 as well as x2.
Sir, this
Yeah.
is a question in Zetli book,
Okay.
and they are taking the bra psi 1 ket psi 2 is equal to 0,
Hmm.
and thus it will give a result.
Hmm.
But when we are taking psi 2 first and psi 1 second, we will get the just the conjugate of the other.
Correct.
So
Now, if it is 0, then it is 0 only, 0 only, right? They are
I
also,
I'm saying about the value for m.
what is your M? I did not understand what is M.
Sir, it's the ket is an expression like a psi 1 plus b psi 2 plus c psi 3 like that.
Okay,
And psi 2 is also another expression with some values.
okay.
So they are saying that find the value of m.
So what is M? M is a coefficient
Okay,
of,
sir. I will read the question.
uh,
Hello.
yeah, yeah. Go
So
ahead.
so the question is, consider two states ket
Hmm.
psi 1 equal to 2i ket phi 1 plus ket phi 2 minus a ket phi 3 plus 4 ket phi 4.
Okay, so let me just write down 2I phi 1.
Phi 1
Then
plus phi 2
phi 2
minus a phi 3
plus
4 phi 4.
plus 4 phi 4.
Yes, sir.
This is your psi 1.
Yes, sir. And the next ket is ket psi 2.
Phi 2, you mean.
No, sir, psi 2 psi.
Okay.
And it's equal to 3 psi 1
Uh,
minus I phi 2
hmm.
plus 5 psi phi 3
Hmm.
minus 4 phi 4.
Okay. So now what is the question?
Where ket phi 1, phi 2, phi 3, phi 4 are orthonormal kets,
Okay.
and where a is a constant.
Okay. They are
Find
orthonormal means phi I phi j is delta ij.
yes, sir, they are orthonormal.
Okay.
Find the so they are asked to find the value of a.
Okay. Such that psi 1 psi 2 are
Yeah,
orthogonal.
yes, sir. And there and in the Zetli book they took for the inner product bra psi 2 get psi 1 equal to 0. They take the condition as well.
Okay.
And they find value a is equal to 7i minus 4 by 5.
Hmm. So that is, if you take this psi 2, if you take this, then you will have 6i. This is minus I plus I minus 5a and minus 16. So that is 7i minus 5a minus 16 is equal to 0. Or 5a is equal to 16. 7i minus 16. A is equal to 7i minus 16 by 5. Is that correct?
Sir, in the ket psi 2, it is not 4 5 4. It is just 5 4.
Oh, it is just 5.
Yes, sir.
Then this is 4.
Yes, sir.
7i minus 4 by 5.
Yes, sir. It's the answer given by them.
Okay.
And I'm asking what will happen if the psi 1 ket is taken first and psi 2 and
Yeah. So if you take that, what will happen? Then you will, that is, if you take psi 1, psi 2, that also will be definitely 0. Okay.
yes,
But
sir.
what
But
what
it
we
will.
will get is that A star.
Yes, sir.
Correct. So that
Yes,
will
sir.
be like 2i will become minus 2i, and hence this becomes minus 6i. Okay. And this is minus I, and this is minus 5a star. Okay.
Yes, sir.
And this is minus 4. So you will have 5a star this will be equal to 0. We have 5a star is equal to minus 7i minus 4, or a star is equal to minus 7i by 4 into 5. It will be same as this. If you take a complex conjugate of this, then you will get this.
Sir, the question said that A is a constant.
Yeah. The
So,
constant, the complex number, no?
sir, it is said so. A is a constant.
Yeah, constant, but constant need not be real constant. No, it is a complex number, right?
Okay, sir. For the same question, the both the A values are accepted.
No. What I'm saying, your A is, we got A as 7i minus 4 by 5, right?
Yes,
What
sir.
will be A star? A star is minus 7i minus 4 by 5. So if you take psi1, psi2 is equal to 0, you get A star. If you take psi2, psi1 is equal to 0, then you get A. But once you get A, you can go to A star, and if you get A star, you can go to A, no?
Okay, sir.
So the same answer basically.
Okay, sir. I understood.
Sir, this question can be solved much easily, no, sir. Like we can take this normalization condition of the first one itself, psi one star psi one, and we can just find A because all other coefficients are given. So it's just that psi one star psi one, and we can find A from that, no, sir, from normalization condition, isn't it, sir?
Yeah. That is fine. But I think in the problem they did not mention whether psi1 is normalized or not. They only said phi 1, phi 2, phi 3, phi 4 are normalized.
Sir, actually, they said that psi 1 is just orthogonal with psi 2, not orthonormal.
Correct. So that is why that information is not there. So if you do that, do you get the same result? 16 a square. But the problem is, since a is a complex number, if you use normalization, you will lose the information about the phase. Okay, so you will not get a complex number. You will get only mod square of a.
Yes.
So you will not get the complex number a from that.
Sir, I have two doubts, sir. Okay,
Yeah.
someone is asking. I'll wait, sir. Someone
Yeah.
asks, I'll wait.
Yes, sir. It was me.
Go
Excuse
ahead.
me, sir.
Yeah.
Sir, I have a few doubts. Like my first question is like this: we are getting indeterministic nature in quantum mechanics. Is it because that we are unable to produce coherent states?
What do you mean by coherent states?
Like as in the two example which was shown by you. Like in the second, we are getting a deterministic result because all the states wave function was same.
Correct. No, the
So
state.
that's why we are getting a deterministic result. But in the another example, you shown that since the wave functions represented them were different means their state was different. So we are not getting a deterministic result. So can I say that we are getting like quantum mechanics overall is indeterministic because that's not deal with coherent states or same state?
Okay, I think I'm not sure if you are using the meaning of coherent state in the way that is used in quantum mechanics, but even though now I understand what you mean by that, but let me try to make this point. First, when I talked about a case where A is dispersed in psi, then also every particle that is coming out of the source is in the same state psi. There is no dispersion in the state. Where is the dispersion? Dispersion is in the measurement results. Okay, the state is same. That is why I wrote psi to every particle that is coming out of this source. The input state is same, which is also same here. Instead of psi, I have phi j, phi j, phi j, phi j like that. What is the difference between these two? Here, this psi is not an eigenstate of A, and hence it, it can be expanded in terms of the eigenstates of A. So this psi is a linear superposition of eigenstates of A, and this is just an eigenstate of A. If you have if the state of the particle is an eigenstate of A, then the result of the measurement is going to be that eigenvalue. There is no other result that is possible. But if you say that your state is a linear superposition of eigenstates of A, now every eigenvalue corresponding to the eigenstate that is there as a superposition will have certain probability. That means you can have different results when you actually make a measurement. So the dispersion is in measurement results. It is not because we cannot create or we cannot create the state to be in phi j or anything, because we want to have we want to understand what happens in a given state. It is not that we are going to prepare the system, or we can prepare the system in a given state. There is no problem for that. But given an arbitrary state, what is the situation with respect to measurement of a property? If you ask that question, in general, given an arbitrary state, which need not be an eigenstate of the corresponding Hermitian operator, then the results are in general dispersed. And when the results are dispersed, we will not be able to make any prediction about the result. We can only talk about probabilities of the results, and probabilities by no means that we can predict. So this is the indeterminism. Okay, so it's not because of what inability we have to create this state in this particular eigenstate or not. This is the structure. This is the nature of quantum world. Okay, now it is a good question to ask: what is the origin of this indeterminism? Okay, and that question is not going to take us a long way into getting an answer, but definitely it's a good question to keep in mind.
Okay, sir. And I have another question, sir.
Yeah.
Like whether the mod of square of all the eigenvalues for a given state, like C1 square plus C2 square, all the probabilities, like whether their sum should be
Sorry, 1
one.
minute.
Like
They are not eigenvalues. They are basically components.
so
Eigenvalues are
here what the result that A and with that probabilities that Cn
yeah.
Cn square.
Hmm.
So whether they are all this C1 square C2 square that need to be one.
Yes. Sure. I think I didn't write it. It's good that you mentioned. So your Cn square over n has to be equal to 1.
So why this need to be followed, sir? I want to understand that.
What do you mean by why this needs to be followed?
Like I mean to ask that, like, why all this? Like, because when we do a experiment that with a meter, like physical experiment in a lab, that
Hmm.
result did that in front of my eyes, that result is definite. Like that result need to be come. But now when I am taking it that into quantum mechanics, like
Hmm.
my this result may be influenced by some other component. Like say, like suppose my answer need to become C2, but here when I am talking to if like probably this Cn square mod is should be 1, then why that C2 value should be affected by C1?
No, C2 value is not affected by C1. Okay. So let me put it this way. If suppose if the state is fixed, let us say, so psi is fixed, okay, then all the Cn's are fixed. Because this is a mathematical exercise. No, you are going to take psi and then write it in terms of the eigenstates of A. Then the Cn's are fixed. Okay. Now see what is mod Cn square? Mod Cn square is the probability that you will get the result as An. Correct. That is the probability that you get the result of An. Now, since I said the result is going to be one of the eigenvalues, what eigenvalue you will get as the result you don't know, but you are guaranteed that it will be one of the eigenvalues. So this statement is saying that it is going to be one of the eigenvalues. Mod Cn square sum over n is equal to 1 means that result is going to be one of the eigenvalues. That is for sure. Now, which eigenvalue we do not know. We only know the probabilities of those eigenvalues. Okay, so probability statement is always statistical in nature, right? I cannot say that what will be the result, but what I can say, okay, so suppose let's say coin toss is probability is half. I cannot say what will be the toss of outcome of the next toss. I can only say if you toss 100 times, on an average 50 times you will get head. Okay, and that also is not sure. You will have some fluctuations. Okay, there will be fluctuations, but you can only talk about average behavior. You cannot talk about individual tosses. Okay, you say that if you toss 100 times you will get probably 50, but if you say that if you toss 1,000 times you may get 500 in a much better chance than 50 in 100. So in the same way, if you take 1 million, 500,000 of them will be heads in a much better chance. So like that, you can only make statements about the probabilities. That is why I came to this description of having a source and sending you a series of, I mean, a kind of beam of particles. On each particle, I will do measurement with a meter, and then I will collect all the results. Then the probability that AJ is result means how many times AJ comes in the total of n measurements is a measure of, this is called frequency interpretation of probability. So how frequently AJ is coming depends on the probability of AJ. Okay, so this is the structure. It is not that some result is affected because of the presence of other. That is, in this particular case, you have a linear combination of different eigenstates of A. Okay, so what is going to be the result? That is why I said, if you are worried about the mechanism of this indeterminism, that's a different question. It's a good question, but uh, we are not very. Uh, there is nothing that I can offer so concretely about that question to you, but it is a good question to keep in mind and periodically discuss.
Okay, sir. And I have one more question, sir.
Yeah.
Like we talk of that psi square, the probability of wave function in a given volume should be one. Like overall
Mm-hmm.
integral should be one. Sir, I can understand. Okay, that's a physical need, because if a particle is existing, it should be exist somewhere in that particular volume. That's why it's
Mm.
taken one. But sir, do we have any mathematical proof for that? Okay, that's equation must satisfy mathematically, or is this it exists just because of our physical need?
Essentially, mathematical idea is something like this. Suppose that is what I told you last time, that if you consider that state as a direction in the Hilbert space, now this is like a unit vector in that direction. So normally, if you say you are only interested in different directions, you are not interested in different vectors along the same direction, right? So when you consider normalized states, you are only taking about unit vectors in that direction. Any other vector in that direction will be multiplied by some scalar to get to get that length.
Okay, sir.
Yeah.
Okay, sir. Thank you, sir.
Sir, what Samarth asked in that question, the summation sin square is equal to 1, it should be 1. So can we relate it with the probability that the total probability should be 1? We can see it as in this form.
Yeah, that's true.
Sir, I have a question.
Mhm.
Sir, while taking the second postulate of quantum mechanics, if the physical observable of a quantum mechanics system are represented by self-adjoint operators. So while we're talking about the self-adjoint operators, we are considering the Hermitian operators there. Sir, my question is taking Hermitian operator in this case it is necessary all the time for physical observables?
Yes, that is necessary.
Hello?
Yeah, that is necessary. But what is the question? Why is it necessary? Is your question?
Yes, sir.
Okay. See, the point is that we have to start the theory with certain physical basis. Now, the physical basis of the theory in this particular case is that so The only understanding that we started with was that there is some kind of a wave nature for all the particles. Now we don't understand what kind of wave it is, but we initially thought it may be a wave that we are familiar with, but later we recognized that it is not so, and then came to this conclusion that it could be probably something like a probability wave and things like that. Now, when you take, for example, let's say that you have let me put it this way. So suppose I have a particular operator A. Okay. Now I want I have a state psi, A psi, and now I ask a question: what is the probability? What is the probability that A has a probability that a measurement of A gives the value AK. Suppose if I ask this question, now I can say that, so let us operate this A on psi. Okay. Now psi is not an eigenstate of A. So I can say that this psi can be realized as A acting on. So normally what happens is A on psi can be written as some phi. In general, this is what happens. Psi will be taken to some chi. Now in this chi, I want to know what is the probability of getting AK. So corresponding to AK, we know that A on this state phi k is equal to AK. Right. This is the eigenvalue equation for the eigenvalue A, eigen equation. Now you can ask a question that what will be your projection of this I? Okay. What will be projection of this chi on this wave function phi k chi? In other words, it is like you ask a question: what is phi k A acting on psi? But now you can say that this can be written as phi k A. Now this psi I can write it as sum over n Cn phi n. Okay, sum over phi n Cn phi n. But A is, so this can be written as phi k. A acts on each one of them. What will you get? So I can pull the summation out. I get simply an phi n. Now an is a constant, so I can pull that out. So Cn, there is a Cn also. So I get Cn an, okay, and phi k phi n. This is an orthonormal basis. So this will be equal to nk. That means I have ck ak. This will become delta nk, and so the summation will be valid only if n is equal to k. So it will be ck times ak. So essentially, I have to have a situation that these kind of matrix elements, okay, so this kind of matrix elements, okay, are related to what is called the probabilities. Okay, so this is actually modulus of I think I'm missing this calculation. So let me not. Uh, I will show the correct calculation. So what I'm trying to say is, you can have something like define something like relative probabilities. Relative probabilities. Okay, that means if you have some state, okay, in this state there is some probability that you have um, you have AK, then you have some other state. What is the probability that if you measure A in this, you get AK you get, and you measure A in the other state, you get AL. Like that, you can talk about some relative probabilities, and they have to be real. Essentially, it means that if you have an operator A, okay, and then you try to write down that as a matrix. Okay, if you have an operator A and you try to write down that as a matrix, the diagonal elements of the matrix, okay, that means matrix like for any basis, okay, for any basis, let us say that basis is some chi j, any basis is chi j a, chi j, okay. So these have to be real. These have to be real. Now this demand that these probabilities have relative probabilities have to be real is one property that is there only for the Hermitian operators. If the operator is not Hermitian, then the diagonal elements with any basis will not be real. For an arbitrary basis, they will not be real. And once we have this, then the eigenvalues of the Hermitian operator are real, eigenfunctions are orthogonal, then all those things will fall in place. So essentially, the wave nature of the particle is related to probability, and probability is related to the requirement of choosing a Hermitian operator.
Okay, sir.
Sir, is it
Hello, sir.
equivalently we are saying that the probabilities are, is it, sir? The
What?
probabilities has to be, like you are saying that the probability number should be something real, not imaginary. That's what you're telling in a whole,
Correct.
isn't it, sir?
Yeah.
Hello, sir.
Yeah.
One of my classmates asked about indeterminacy in quantum mechanics. Sir, is it due to the uncertainty nature of space-time itself in
Uncertainty
microscopic
in what?
dimension? In space-time, in microscopic dimension.
That's what. So what I'm trying to say is that the origin of indeterminacy is something which is very deeper question. Okay. So I do not want to talk about it now, but if you don't want to ask that question about the origin of indeterminacy, but the postulates of quantum mechanics tells you that such an indeterminacy is a reality, you have to live with it. All that you can do is only to talk about probabilities, but you cannot talk about what is the exact answer.
Yes, sir. As we zoom into the space-time, the more we go closer to Planck scale, these fluctuations goes wilder and wilder, and when we operate an operator, we get different values. Is it right?
So that could be one. That could be one direction in which you can search for the origin, but I do not
Yes, sir.
know for
Yes,
sure.
sir. Thank you, sir.
Excuse me, sir.
Yeah.
I
Sir,
have one more question, sir.
Yeah.
Like, sir, when we find, like, when we solve this question, what is the component of momentum along F in a position basis? And as a result, we got the basis to be e power ikx, right?
The function to be
Now,
power.
sir, yeah, e power ik. Now, sir, I don't know, but I'm not very sure of this question. But I just feel there should be associated time component also with the this thing. Like we should also be taking time evaluation on this as a
Yeah, yeah,
basis.
correct.
So
You are
why
right.
that is not there, sir?
Yeah, yeah. So you are right. So I, in fact, thought that I will complete that part today, but I could not complete. But we are going to bring that time part soon. Okay, right now, for simplicity, I have completely ignored the time part and I have frozen the time as if time is not moving at all. But we cannot do that. We have to bring in the time and then talk about how things change with time. And that was actually a part of my agenda today, but I could not complete. So we will do it in the next class. But you are right, we should bring in time.
Okay, sir. Okay, sir. Thank you, sir.
Yeah. Any other question? Ritesh, you had some questions?
I have actually like a threefold out. Like one
Ah.
is like when you said that eigenfunction of a Hermitian, Hermitian operators are real. Sorry, or
Hmm.
orthogonal.
Hmm.
Orthogonal. You meant for discrete eigenvalues or for the not for also the same eigenvalues, the degenerate eigenvalues, because
No,
that
they have to
question.
be the general proof which I wrote down yesterday is for
Hmm,
the distinct eigenvalues. That means they all
yes,
have to be non-degenerate.
yes,
But what happens if they are degenerate is what I tried to discuss today.
yeah, subspace. We get a
Yeah,
subspace.
yeah. We had a
So
subspace
which
and you can choose orthogonal vectors in that subspace.
okay?
So
So basically,
as a
uh,
result, if there is non-degeneracy, then they are orthogonal by theorem. And if there is a degeneracy, you can make them orthogonal. In such a way, I have shown that for every Hermitian operator, you can construct an orthogonal set of eigenstates, which will form a complete orthonormal basis for the Hilbert space.
uh, uh, sir, I think we can also do it by Gram-Schmidt orthogonalization process, isn't it, sir? For any two
Correct,
vectors, we can. Yeah, that
correct,
is another
correct,
one process, isn't
correct.
it, sir?
Yeah, I did not dwell on how to do it, but one way to do it is using Gram-Schmidt orthogonal process, orthogonalization process.
Sir, and the second doubt is when you say that I have the doubt with the first interpretation of this processor, when I try to find the p operator as a e power ikx.
Hmm.
In the first interpretation, you said wave with fixed p. I mean,
Hmm.
can you show some light on that, sir? Because that part I was a little bit confused. How did you come to know that something is fixed? How did you say that P is fixed with that XP? I mean, this inner product of XP. How you're telling it that way P is fixed?
No, essentially, when I say momentum eigenstate is a fixed momentum state. No, just like so, if I have this P here, so this is like I have a momentum operator P acting on this P will give me an eigenvalue P and P. So this is the statement of a momentum eigenstate. That means the
Ah, yes,
eigenvalue is fixed.
yes,
So for a
yes,
fixed P, I am here in the first case, I am trying to present a physical argument that if you fix P, okay, then you have fixed lambda. And what kind of a mathematical expression can we have for a wave representing with a fixed value of lambda? So that is simply a plane wave. Basically, a sine
yes.
wave. In the complex notation, it is called a plane wave.
Okay, sir. Sir,
So
and
this
regarding with this probability, yes,
yeah.
sir, go ahead, sir.
No, what I'm saying is we have presented this argument earlier also once when I was trying to motivate Schrodinger equation. So where we said, I mean, I think I have spent a little more time during that time, how this physically we consider this a plane wave. That is why I think I didn't spend much time today. So maybe if you want, you can look at one of those old lectures where I talked about how to obtain, I mean, argue for Schrodinger equation.
Ah, okay, sir. So my last doubt is like it is a little bit heuristic. Like what I'm
Hmm.
telling is, somebody told that, I don't know who is that. Somebody told that this why this summation of Cn square is equal to 1. I think it's Samarth, if I'm right. So that my question, my answer will be like, what I thought is basically we defined what is probability. We defined the probability should be 1. So only we are like asking it summation to be 1. If we had defined, like the mathematicians in those days defined it to be 100, we can also take it to be 100, and we can form form and formalism based on that, isn't it, sir? It's like
Yeah,
something we define the probability is 1. So that is the reason why we are like making it forcibly that summation should be 1. If the probability is defined to be some other number, we can also define the whole, reformulate the whole theory in saying that that summation should be equal to that number. It's like that, isn't it, sir?
yeah. In some sense, it is like that. But what I'm trying to say is that see, the probability theory is something which is independently developed in mathematics or statistics, whatever you call, and that has certain rules. Similarly, linear algebra is independently developed by mathematicians, and that has some rules. So now what we are trying to do is we have some physics here. There is a requirement to describe electrons, to describe spectra, to describe transition probabilities, to describe various interference and all those things. Now we have made certain observations. We have some experimental results. Now we are trying to see if we can use these elements of mathematics to build a foundation for the theory. Now, when we are using this, we have to completely respect the structure of that mathematics. In that sense, if we say probability, the total probability has to be equal to 1. Now, somebody may ask, why should you use probability here? That's a different question. Then we are not talking about this theory. In this theory, probability is used, and there is an evidence that probability makes sense, and hence we have to use the rules of probability. For example, if you take, so I did not talk about n particle system here. If you take an n particle system, and if you talk about wave function for each particle, then the n particle system wave function can be written as a product of these wave functions. And when you try to normalize that wave function, many times the normalization which people follow is that normalization of the n particle wave function is not equal to 1, but it is equal to n. Each particle wave function is normalized to 1, but n particle wave function is normalized to n. So such things are also people use it. But it is not at variance with the definition of probabilities.
Yes, sir. So now it makes me to beg the question that what is the fundamental difference between classical probability and quantum probability?
Yes,
I mean,
that's
this
a
is
good
something.
question. That's a good question, and I want all of you to think about this. Is it same? That is, whatever probability that we use in statistics, whatever probability that we use in statistical mechanics, is it same or is it different? That's a
It's
good
different.
question to
That much
ask.
I'm sure. It is different, and that much sure. And Dirac has shed some light in his book, but I'm not able to understand it completely. In his first 30 pages, he has tried to explain this, but still I'm not able to understand it completely. So maybe one day we can shed some light. That was my outcome. I tried to differentiate between what is classical and quantum probability, but still I'm under some confusions. So this is something which we can.
Actually, I think one difference, I'm just trying to give a hint. One difference is that in classical physics, probability, wherever it is used as a fundamental input to the system, to the theory. For example, in statistical mechanics, if you say that I don't know what the state is, or in a coin toss you don't know what the outcome is, then you say that that ignorance is actually, or information theory, for example, you have some ignorance, and the ignorance is quantified in terms of probabilities. Their probabilities enter into the theory as fundamental quantities. Only in quantum mechanics, probabilities are not fundamental quantities. Probabilities are derived quantities. So that is the major difference. There is a major difference between probability in quantum mechanics and probability in other subjects. Here, probabilities are not fundamental quantities. Fundamental quantity here is the wave function, or what is called square root of the probability. We cannot say exactly square root of the probability amplitudes. Now, this is the fundamental quantity, and probability is only derived from that. Okay, so that is one major difference between
Difference.
the probability in classical physics and quantum physics. And because of that, we do not know whether this probability business that comes in quantum mechanics is an ignorance based. That is, we do not know some information, and that is why we have to use probability. That much is very clear in classical physics. We do not know some information, we have no access to that information, so we have to use probabilities. In quantum mechanics, whether such an ignorance is the cause of using probability is not clear. We do not know or we cannot know. So that is that's a big question which still is being debated.
Yes, sir. Sir, and last thing is like this is a very like I don't know if it's a silly question. Sir, I'm still not convinced with the proof of this linear independency, sir. So if we can somewhat prove it in a short sense, I'll be more happy. Like, I'm still not convinced with the linear independency of vectors. How it is that the vectors are equal to summation is equal to 0. That part I'm still a little bit confused with that proof part. So that will fulfill my wish. Yeah. Thank you, sir. Yeah.
The definition of linear independence is, suppose you have, let's say, vector v1, so let's call v1, v2, and let's say some vn. So this set of vectors are linearly independent if if you have some scalars alpha 1 v1 plus alpha 2 v2 plus etc. plus alpha n vn is equal to 0. Okay, this implies alpha 1 is equal to alpha 2 is equal to all these alpha n are equal to 0. This is the definition. Okay, this is the definition, and you have to use the definition if you want to show whether any of these n vectors are linearly independent. Now, how do we argue this? Okay, let us say that this is linearly independent even if this is not equal to 0. Okay, let's assume that. Okay, that is our v1 etc. vn are linearly independent, but let us say that one of these alpha j is not equal to 0. One of the alpha j is not equal to 0. Let alpha j not equal to 0. Then what happens? I can say this alpha j vj can be written as alpha 1 v1 plus alpha 2 v2. So I will write it like this. Sum over I is equal to 1 to n alpha I vi, and of course I is not equal to j. Correct. So that means what? That means I can write this vj as a linear combination of I other n minus 1 I not equal to j, n minus 1 vectors alpha I by alpha j. What does that mean? Vj can be written as a linear combination of other n minus 1. That means this is not, this implies this set v1 etc. vn is linearly dependent, because I can write down 1 in terms of the n minus 1. So this is linearly dependent. So this is a contradiction to our assumption that it is linearly independent. Okay, so that is the way to understand that if it has to be linearly independent, then all the coefficients have to be equal to 0. So the only way of a linear combination equal to 0 is that the coefficients have to be equal to some all the coefficients have to be equal to 0.
It's individually has to be like alpha 1, alpha 2 individually has to be, not a summation should be 0. Yes.
No, individually. Each coefficient has to be 0.
0, yeah. Like last time, why I got confused because I forgot that we are proving it by method of contradiction. I was like looking at it again by the normal method, so I was a little bit lost. Okay, sir. Now
Yeah.
I'm very much clear. Thank you so much, sir.
Yeah.
Yeah.
Okay. So I think if there are no questions, then
So one more thing.
yeah.
So at the end, you showed us a experiment where we have a source and some particles are coming in the same state.
Uh,
So do we have such experiments in practical also, like practical real life? And if there
yeah.
are,
Yeah.
if
We
there
can.
are, yes, if there are
Okay.
such
Go ahead.
experiments, so
Hmm.
you said that the probabilities will become equal to the n by nj by n thing when the n tends to infinity. So we have to do the experiment or the at least the measurement n tends to infinity number of times, but that is not possible in real life. So how do we get bypass that?
See, physically, the infinity is always some large number, and how large is always determined based on how convergence is taking place. Suppose let's say that you want to determine the probability. Let's say probability is 0.7. You want to get zero point 0.7, then your n may be something like 500 to 1000. No, I want my probability to be 0.75. Okay, you want up to 2 decimal accuracy, then you have to use a bigger number n. You want 3 decimal accuracy, then you have to go much higher number. So the probability is a real number which can be determined up to some accuracy.
Hello.
Depending on what accuracy you want, you have to use the number to be accordingly large.
Okay, sir. Sir, what kind of experiments are there, like quantum experiments, which verify this? Like as you said.
See, some of the experiments that you can verify this one are done using the Stern-Gerlach experiment, for example, where you talk about spin half particles in beam coming, and then because they are easy to verify because you have spin operators which has only 2 eigenstates, so it's easy to handle. Okay, so one set of experiments are using the Stern-Gerlach experiments, but people also have done some more serious real quantum mechanics like experiments. Okay, that those experiments are also there, but these experiments can be done. You can actually produce a beam of particles and then look at each particle and then do a measurement on each particle. In fact, when people had this kind of arguments, it was more or less thought experiments. Now I think these experiments are all realized.
Okay, sir. Thank you, sir.
Any other question?
So, excuse me, sir. Like, I have one last question, if time permits.
Yeah.
Like, we talk about eigenfunctions, and we talk about like two eigenfunctions, let it be phi 1 and phi 2, and then we saw that these eigenfunctions can be represented into other eigenfunctions with proper coefficients, right?
Hmm.
So, can I, like, as you've shown us in the board, that phi m1 is phi m1 and phi m2 are they are represented as c1 phi m1 plus c2 phi m2. Like phi m1 is equal to some like this.
Hmm.
So, can I also represent the eigenfunction? Let it be phi 1 is equal to c2 of c2 c or some constant multiply into phi 2. Can I directly relate two eigenfunctions with coefficient without addition?
That is, if phi1 is an eigenfunction with an eigenvalue a1, some c times phi1 is also an eigenfunction with eigenvalue a1. No, there is no problem because that is in the same direction.
So if that's true, sir, then like whether can I make it like can I make a statement that all the functions are interrelated with the coefficients?
Yeah. So essentially you have to take this clue from what I discussed. Suppose let's say you have a non-degenerate eigenfunction. Let's say eigenvalue is non-degenerate. That means there is only one function associated with that eigenvalue. That means you can essentially talk about the span of that one function will actually be a one-dimensional vector space, which will be a subspace, but it's a one-dimensional vector space of the Hilbert space. Now, every vector in that is a multiple of the phi 1. You understand, no? That is called one-dimensional subspace. Now, if I have two functions with the same eigenvalue, then the eigen subspace will be two-dimensional vector space. Okay, so in that sense, it is natural to expect that a one-dimensional subspace will be there with respect to every eigenfunction if it is non-degenerate.
Okay. Yes, I got the ideas. Thank you.
Okay, so then we will close.